Okay, we are close to the end. The last guest of today afternoon is Davor Kumozec, and he will talk about a new numerical scheme for the transport equation in 2 dimensions. Okay, so I leave the floor to you.
So thank you for introduction. I will talk to you about my work in collaboration with Berenice Grek and your panel. The title is Numerical Scheme for the Transport Equation in 2 Dimensions. First, I will tell you about the context of our work. After that, I will give you a formulation of the problem, explain numerical scheme in 2 dimensions, and show you some numerical examples. So our goal is to extend some previous works in 1 dimension to 2 dimensions, satisfying maximum principle. This scheme is based on the method of characteristics. We will use variable velocity on Cartesian mesh, which contains only rectangles. We will use 6-point stencils to reach order 2, polynomial of order 2. And I will explain you later why this scheme is unconditionally stable. So transport equation, you know, it appears in fluid dynamics, in Navier-Stokes equations, and so on. Our domain will be rectangle, and we are looking for numerical approximation of the equation of this form. H is our unknown function. V is a velocity field, so it's a vector. And velocity is known, and both of these 2 functions can depend on time and 2 spatial variables. We will have initial condition, which is h at time 0, and boundary condition defined on the part of the boundary depending on from where velocity is incoming. So now about method of characteristics. You know that we can use method of characteristics to show that, for example, transport equation has a unique solution, and we want to use that idea in numerical purposes. So instead of solving 1 PDE, we will solve 2 ordinary differential equations. First one defines the flow C, through which particle moves, and the second one shows the behavior of function h along that characteristic curve. In our case, you see that on the right-hand side we have 0. So in our second equation here, f is equal to 0, and in this case, this second ODE is equivalent to an interpolation step. So what are the steps in our numerical scheme? So MOC consists in these 2 steps. First one is computation of the foot of the characteristic curve, and this is related to the first ODE. And the second step is interpolation, and that's related to the second ODE. Now a little about notations. So t will be between 0 and capital T, which is the final time, and t is the number of nodal points in time, and delta t is a time step. Also in spatial variables we have nx and ny, number of nodal points, and delta x and delta y mesh sizes. Here is the short notation of function h and velocity field in nodal points. So first step, we want to compute the foot of the characteristic curve. For the second order approximation, we have this expression. This is a vector of dimension 2. Even if derivatives of velocity field are known, we can use approximations. And for approximations of those derivatives, here is given an expression for foot of the characteristic curve in x direction, and similar is for y direction. Of course, we can use CFL condition, or current number, to provide better accuracy of the scheme, but stability of this scheme does not depend on this condition. Why? Because if you look better here, we have just error which depends on the time step. And in this second step, which is approximation of function h at foot of the characteristic curve, we will have only error which depends on space steps. So what we have to do here, we have to find indices q and p, where foot of the characteristic curve is located. And when we find them, we can introduce theta x and theta y. That's a number between 0 and 1, and they show us location inside of location of foot of the characteristic curve inside this rectangle. And for first order approximation, or first order polynomial, we have this expression. This is a convex combination of these 4 points, because it depends on theta x and theta y. Both of them are between 0 and 1. And if we want to go further to the second order polynomial, we have polynomial of this form. Here, alpha 1, 2, and so on, till 6, are computed in the way that this is an interpolation polynomial depending on the 4 possible stencils. So we use always these black 4 points and additional 2, for example, these 2 blue or red or green or purple points. So we have 6 point stencil. And what is the strategy for interpolation? So we want to satisfy maximum principle. That actually means that we want from our next iteration of h to be between these 4 points. This prevents oscillations, appearance of oscillations, and preserves positivity. And what is the strategy? So first we check for second order polynomials for all 4 possible cases. Are they satisfying maximum principle? So if none of them satisfies this condition, we will use linear approximation, because we know that linear approximation always satisfies because it's convex combination of those 4 points. If just one of the second order polynomials satisfies this maximum principle, we will take that one. Or if there is more than 1, 2, 3, or 4, we will use average value between them. So if we have 2, for example, we will use both of them with weights 1 over 2, 1 over 2, or for 3, 1 over 3, 1 over 3, 1 over 3, and so on. And now I will show you some examples. First one is sign initial condition. Domain is, in time we go from 0 to 2 pi's. Domain in space is from -1 to 1, and from -1 to 1. Velocity field is y minus x. That means that this initial condition will go in circle. So after one term, that's after 2 pi times, we will be at the same position where we started. And on the right picture, you see a solution after these 2 pi times. And okay, here we can see that the sign initial condition is constructed in the way that it's equal to 2 here at the maximum point, and outside of this hat is equal to 0, identically equal to 0. And after one term, we can see that we have 1.81. So we have lost a little bit of its maximum. It should be the same, so we don't lose mass in theory. But of course we have numerical scheme which is on rectangles. Shape is maybe not, shape of this function is maybe not the best to approximate it with rectangles, yes. And here I will just want to show you the order of convergence compared with ENO scheme. ENO scheme is also adaptive scheme, which chooses polynomial in the way, so we have here 4 possible polynomials. ENO scheme will choose that one which has the smallest absolute value of differential quotient for all of them. So if differential quotient is minimum, we will use that one. And the blue line is for the ENO scheme, red one is for MOG scheme, and here is, okay, this is log-log scale. So this one is y equal to 2x. So if it's of order 2, it has to be parallel to this one. We see that our error is smaller than for ENO scheme, and we can see that it is almost parallel to this one, so that means that we have second order of accuracy. In the next example, everything is the same except that now we have Gaussian initial condition. The difference is that here, outside of this hat, we don't have identically equal to 0. It decays very fast, but it's not identically equal to 0. And in this example, we see that we lost more than in previous example. Here, maximum is 1. After one term, we have 0.66. So this is one of the things which we can try to improve in future work. And here is the order of convergence. Again, compare with ENO scheme. We see that here we have a little bit more than the second order of accuracy, because I believe that with better choice of those coefficients in when we have more than one polynomial admissible, we can get more than second order of accuracy, but with this stencil we can reach order 3. And for conclusion and future work, so I showed you extension of one-dimensional scheme to two-dimensional scheme based on method of characteristics for transport equation. It's at least second order accurate. We saw it on these 2 examples. And it's unconditionally stable, and that means that it prevents positivity and prevents appearance of oscillations. And for future work, we can try to extend this to non-homogeneous transport equation when we have this F source, and to try to extend it to other convection type equations like Burger's equation and so on. Mass loss reduction, the thing we saw here, that we lost something of our initial condition after just one term, after 2 pi times, and try to find better choice for coefficients in a convex combination of when we have more than one admissible polynomial. And here I have references. So for the first, for the 1D scheme, and for the ENO scheme in this second reference. And thank you for your attention.
Thank you, Davor. Thank you. Very interesting. Okay, I'm asking you if anybody of you has questions for Davor.
So you said that you can escape from the CFL condition, right?
Yes.
How did you manage to do that? Because the CFL condition at the end of the day is actually an analytical condition, right? Because you know that it comes from the fact that you have some sort of information that depends from the entirety of the space, and you have a cone of dependence. But your scheme seems to be explicit, right? So
yes.
how do you escape from this?
So here, if we have, for example, c equal to 1, and if we start from if our characteristic curve starts from this point here, and it goes, for example, like this, here, we know that if we started from here, if C is equal to 1, we will be in this rectangle. Maybe if I show it in this picture. So imagine that time is parallel to this. Okay, so if we start from, for example, from this point, if we have positive velocity, we will end up somewhere here, if C is equal to 1. So we will be in this rectangle. If C is, for example, 2, it can be somewhere here, in this part. So,
so the idea is that somehow your numerical cone of dependence will always include your analytical cone of dependence.
Yes. For example, in this case, I always, when I computed these errors, I always use the same C. Because if I don't use it, I think I can't compare errors for smaller delta x, for example. So it has to be consistent, but for any C in this formula, you will get stable scheme.
Thank you very much.
Do you have a question?
I just want to know if you have some idea on how to solve the problem of the artificial diffusion that makes you losing something in the maximum. Do you have some idea on how to do it?
Yeah, we tried to do that computing fluxes and to, for example, if we have two admissible polynomials, we can try to find this, for example, we have H1 and H2, which are admissible. We have to find optimal, let's say, gamma, which is gamma times this one plus 1 minus gamma times this one.
Relaxation.
Yeah, yes. And we can use, for example, fluxes to determine that gamma, such that flux is reduced. Because if you have a conservative scheme, you don't lose mass. But here we sometimes use this stencil. After that, maybe we will use this one. After that, maybe we will use combination of these three, and so on. So if we use always, for example, this one, we have conservative scheme. So we don't lose mass. But also we sometimes use linear approximation. So that's why it appears. So we want to use to compute fluxes and to minimize the difference between what's coming in and what's going out.
Thank you.
Any other questions? Okay, I think for today we are done, and we thank you pretty much for your intervention.